Sublimation. Sublimation is the transition directly from a solid state into the gas state. A lot of things will not sublimate, but some things do. So if we think about water in ice, the water molecules in ice, because ice is water, these particles do have thermal energy even though it's frozen. So they're vibrating and they're wiggling around. We still have an average kinetic energy based on the temperature. So some of these particles are moving more vigorously than others. And if you have a particle with higher energy that's on the surface, it can break loose. When it breaks loose from that solid, it goes into the gas state and floats away. That's called sublimation. Deposition is the opposite. That's where you have a particle that was in the gas state going directly to the solid state as opposed to condensing into a liquid. Okay, so because of sublimation, solids can also have a vapor pressure. Usually the vapor pressure is extremely low, and so we don't even need to think about it. But some solids have significant vapor pressure. Dry ice. So here's a photograph of dry ice, and it looks like there's all these swirly things coming out. So what's happening with dry ice is solid carbon dioxide. And the reason it's called dry ice is because it doesn't melt. Regular ice melts and gets everything wet. Solid carbon dioxide sublimates, doesn't get anything wet, and so that's why we call it dry ice. What we're seeing here is not the carbon dioxide that's coming off in the gas state. We're seeing the cold carbon dioxide causing the water in the gas state, in the air, the humidity, to condense. And so it's making these little clouds. But you can't actually see the carbon dioxide itself. So carbon dioxide, really fun stuff. Regular ice also sublimates. Have you ever noticed that old ice cubes that you find in the back of the fridge are smaller than they were when they were first made? We have an automatic ice maker, and every once in a while it gets jammed up or something happens, and you pull out the bin and there's ice cubes stuck that haven't been coming out, and they've just been sitting in there for a long time. And they're smaller than the rest of the ice cubes. That's because they've slowly been sublimating away. It happens at a low rate, but it does happen. And it happens at a faster rate if the container is open. Because then when those molecules go into the gas state, they just float away and they never deposit again. Another way we see this in the freezer is ice crystals in airtight bags of frozen foods. And you pull out a bag of tater tots that you forgot about. Oh, cool tater tots, and you dump them out on the pan. There's all these ice crystals. Why the heck do they package ice crystals with the tater tots? They didn't. That water used to be inside the tater tots. But it sublimates. The water molecules go into the gas state, but they're inside this bag, so they bounce around a little bit. They don't have enough energy, and so then they don't condense. They actually deposit and form these little crystals of ice. So we see food that gets what we call freezer burn. It gets all dried out and hard on the outside, and that's from the sublimation of the water that was in the food. It's leaving. And you can minimize that by sealing the food in such a way that there's no airspace above it, so that there's nowhere for those gas molecules to sublimate to. Yes?
Can sublimation occur in cold temperature at all?
Sublimation occurs for ice at cold temperatures. Ice can sublimate at warmer temperatures, but it's usually pretty busy melting. Now, the colder the temperature, the slower the rate of sublimation. And so that's why one of those sub-zero freezers, the really expensive ones that get colder, you're going to have less sublimation at the colder temperature than you do. You know, if your the temperature of your fridge is like -1 degree Celsius, or if it's -10 degrees Celsius, you'll have less sublimation at -10. Yes?
If you had an increase of vapor pressure inside a freezer, would that prevent sublimation? Or had a freezer specifically designed to keep gas, like a high concentration?
Yeah, if the vapor pressure of water was, I mean, you know, if you had a high concentration of water vapor in your freezer, that would reduce sublimation, but the problem is that that's going to cause a lot of frost buildup, right? Because there's only so much water that will fit into air at cold temperatures. So they talk about relative humidity, because at colder temperatures, air cannot hold as much water as it can at higher temperatures. Any questions? Fusion is the same as melting. So fusion and melting mean the same thing. We understand what melting is. The word fusion is like, I don't know. The way I remember this is I think about chocolate chips. If you put chocolate chips in a pan on the stove and you start to heat them up, they soften and fuse together, right? That's melting. So melting and fusion are the same thing. Freezing is the opposite. Freezing is going from a liquid to a solid. So we see melting a lot more in terms of ice. As the temperature of the ice increases, the average kinetic energy of the molecules increases, they vibrate faster, and at some point, at the melting point, they have enough thermal energy to overcome those intermolecular forces that are holding them together and melt into a liquid. They're still held together by those forces, but they have enough energy that they can slide past each other. So here's an energy diagram. Here we have the temperature increasing as heat is added. So if we take a block of ice at -10 degrees and we add heat to it, the temperature of the ice will increase until we get to the melting point. At 0 degrees Celsius, what happens is all of the energy that we're putting into that goes into the melting process. The temperature will not rise until all of the ice has melted. At that point, we have liquid water and the temperature will increase again. Adding heat faster or adding more heat will cause the water to melt faster, but the temperature will still be 0. Okay. Now, you could have minor differences if you had a glass of ice water, right, and you don't have any stirring. The bottom of the ice water might be a little warmer than up where the ice is, but when you have ice and water together, the temperature will be 0 degrees Celsius. Well, there's energy involved in melting and freezing. Melting is an endothermic process. This makes sense to us because how do you melt an ice cube? You heat it up. You put heat into it. So heat of fusion, it's called heat of fusion instead of heat of melting, I guess because it sounds fancier, but is a delta H fuse, is the heat required to melt 1 mole of a solid. So going from 1 mole of solid water, ice, to 1 mole of liquid water, the heat of fusion is 6.02 kilojoules per mole. That's going to be a positive number because you have to put the energy into the ice to melt it. I live in Reedley, where we have a lot of citrus trees, and in the winter, the temperatures, sometimes we get a freeze and the citrus crops are threatened. Because if your oranges freeze, they're ruined. The cells burst and they're just no good. You've lost your whole crop. So we try to protect against that. You can't just go out and put big space heaters in the groves because, you know, that's going to be super, super expensive. But you can use the energetics of melting and freezing of ice to help protect the citrus crops. So what they do when a bad freeze is predicted is they flood the fields. So there's lots of standing water. So the temperature drops below 32 degrees Fahrenheit, below 0. The water begins to freeze. As the water freezes, it releases energy. Melting is endothermic, therefore freezing has to be exothermic. As the water freezes, it releases energy and keeps the temperature at 0 degrees Celsius. 32 Fahrenheit. I haven't done the conversion, but citrus, if they're at 26 degrees Fahrenheit for like 4 to 6 hours, that's when you're in bad trouble. So if you can just keep it above that, you're okay. So if you've got this water freezing at 32 degrees Fahrenheit, that is oftentimes enough to protect the whole field. And then just to help out, because that's down at the bottom and you don't want the oranges at the top to freeze, you have these big fans that blow the air around. Sounds like jet planes taking off in the middle of the night. Oh, it must be cold, I hear the fans. But that's a very practical local application of this idea. Any questions? Heat of fusion is usually a lot less than the heat of vaporization. Heat of vaporization is the amount of heat required to vaporize, go from the liquid to the gas. When that happens, you completely break all the intermolecular forces because they're completely separated. When you melt a solid, you're just partially overcoming those intermolecular forces, just enough that we can slide around. We don't have to completely break free. And so we see the heat of fusion is generally much less. And here's a graph just showing you that. So the blue is heat of fusion, much less than heat of vaporization. So here's the whole heating curve for water. And it's important that you be able to look at this and understand what's going on here. So here we're looking at a block of ice starting maybe at minus 25 degrees, and we're adding heat. And we add heat, and the ice warms up until it gets to the melting point. And you should know the melting and boiling points of water, 0 degrees Celsius. At that point, it's going to be flat. It'll keep absorbing energy. That energy goes into partially breaking the intermolecular forces so that it can become a liquid. Once it has all become a liquid, then the temperature will rise again until you reach the boiling point. At the boiling point, 100 degrees Celsius, the temperature is flat again until all of the liquid has been converted to a gas, and then the temperature of the gas can increase. Any questions? If you're taking gaseous water and condensing it and freezing it, you're just going the other direction, okay? We have looked individually at how to calculate the energy change for each of these line segments. So this line segment here, increasing the temperature of a given amount of ice, that's MCAT, MC delta T. And we learned that earlier in the semester. So Q equals MC delta T. The mass of the substance times the specific heat capacity times the change in temperature. That's the energy required. And so that applies to any time you have a temperature change. So heating the ice, heating the water, heating the steam. So that's for 1, 3, and 5, those segments. And what we're just learning about in this chapter is what do we do here on the flat portions. This is the heat of fusion. So for number 2, you use the heat of fusion. And there's not really an equation for that. You look at the heat of fusion, and it's usually in kilojoules per mole. So you use that as a conversion factor to take the amount of substance in moles and find the kilojoules. And then for line 4, you're going to use the heat of vaporization. So if we wanted to calculate the amount of energy to take 1 gram of ice at minus 25 to being water at 75 degrees Celsius. Well, we draw this curve, heating curve, even though it's heating line segments, really. There's no curve, is there? And you're going to have an equation. You do a calculation for each individual line, and then you add them together. So it's just putting some pieces together. In this particular diagram, what they're doing is, I believe they're doing 1 mole of water. They're doing a particular mole, a particular amount of water. Yeah, it's 1 mole. So they're taking 1 mole of water from minus 25 to 0, and they calculate in terms of kilojoules per mole for each of these things. So let's do an example. Let's do 1 mole of ice at minus 25 degrees Celsius to steam at 125 degrees Celsius. So we're going to need heat of fusion, heat of vaporization. We're going to need specific heat capacities. Well, they're kind of hiding in this table. So ice warming, this is the specific, that's for 25 degrees. Hang on. Pause. So we do need some values here. So we looked these up. Yeah, got to get a marker here. So the specific heat capacity for ice is 2.03 joules per gram degree Celsius. For water, liquid water, it is 4.184. That's what I meant. 4.184 joules per gram degree Celsius. And for steam, it is 1.84 joules per gram degree Celsius. Then we need heat of vaporization and heat of fusion. The heat of vaporization, I believe, is 40.7 kilojoules per mole. And heat of fusion is 6.02 kilojoules per mole. So that's information that you need before you can do these calculations. On an exam, that would be provided to you. On homework, you might have to look it up. You should be able to find those things in your textbook. So here we've got a lot of processes going on, and so I think it's helpful to draw at least a very sketchy picture to help keep yourself on track. So we're not going to do that. We've got some temperatures in here that we know. So we're starting at minus 25, and we're going to heat the ice up to 0, where it's going to begin to melt. So there's 0, and then we'll heat the water from 0 to, what's the boiling point? 100. And then this says we take it to steam at 125. Those are all degrees Celsius. So I'm just going to number these. 1, 2, 3, 4, 5. There's 5 lines. There's going to be a separate calculation for each of those, and then we just add them up. Okay? This is 1 mole of ice. So the first one, step number 1, we're taking 1 mole of ice and we're heating it from minus 25 to 0. So delta T, the change in temperature, is the final temperature, 0 degrees Celsius, minus the initial temperature, which is minus 25 degrees Celsius. So that's a change of 25 degrees Celsius. With changing temperature, we have the equation Q equals mc delta T. We have C for ice right up here. What's the mass? The amount was given in moles. we need the molar mass to figure out how much grams we have. Well, it's 18.02 grams per mole, and so since it's 1 mole, I can do that calculation in my head. So 18.02 grams times the specific heat capacity, 2.03 joules per gram degree Celsius, times the change in temperature, 25 degrees Celsius. Grams cancel out, degrees Celsius cancel out, and we have joules. 18.02 times 2.03 times 25. So for that one, the amount of energy is 914.5 joules.
Do you want to take any extra decimal places before we add it all up?
Well, but we should always consider significant figures. These temperatures are a little bit iffy, aren't they? So this would have 2 significant figures, and so there'd be 2 there. This one has 3, and this one we did with 4. So I think, being strict, we'd have 2 sig figs, and so that would be right there. And then we've got a couple of extras. Always good to keep track of significant figures. Step 2 is the ice melting. And so we're going to use the heat of fusion, 6.02 kilojoules per mole. There's not really an equation. We have 1 mole, and we're going to just multiply that by 6.02 kilojoules per mole. Our units work out. I'm going to assume that they mean exactly 1 mole, because otherwise it's kind of dumb to do this with 1 sig fig. So I'm going to say that this is 6.02 kilojoules of energy. Okay? The problem's worded kind of sloppy. How are we going to calculate the energy for part 3? Q equals mc delta T again, but now we have a different change in temperature and a different specific heat capacity because now it's liquid water. So we have the same mass, 18.02 grams. Now we're going to use the specific heat capacity of liquid water, 4.184 joules per gram degrees Celsius. And what's the change in temperature?
100 minus 0.
Yeah, it's going from 0 to 100. So we take the final temperature minus the initial temperature. So that's 100 degrees Celsius. 18.02 times 4.184 times 100. 7539. We got at most 4 sig figs there. 0.57 joules.
Can I ask a question?
Yes.
You used 100 degrees, but didn't we heat it to 25?
We're just looking at line segment number 3.
But didn't it come from the temp? Oh, okay.
And so we already took care of this increase in temperature from minus 25 to 0.
Oh, okay, I see it now.
Yeah. And then we did this part, and now we're just looking at 0 to 100. Yeah. That's a good question, because sometimes students are like, well, it went from minus 25 to plus 125. Why don't we do the whole thing? Because the amount of heat needed to heat up ice, water, and steam is different, and so we can't just combine them. Then line segment 4 is where the water is boiling, vaporizing. So we use the heat of vaporization. Again, we have 1 mole of water. I'm using moles there because the heat of vaporization is in moles. 40.7 kilojoules per mole. And so that ends up being 40.7 kilojoules. Now we have all of the water converted to steam. It's still at 100 degrees Celsius because it just finished boiling. And now we're going to heat it up again. We're going to use MC delta T with the heat of fusion for steam, not heat of fusion, specific heat capacity. So 18.02 grams, 1.84 joules per gram degrees Celsius. And what's our temperature change for line segment 5?
125.
Yeah, so it's 125 minus 100, so 25 degrees Celsius. 18.02 times 1.84 times 25. And significant figures, the 125 minus 100, well, the 100 we can consider to be exact. The 125, we'd say, well, that's got 3 sig figs. But when you subtract 100, you're left with 2 here, and so 2 sig figs there. Now what we have to do is we have to take all 5 of these numbers and add them together. But some are in kilojoules and some are in joules. It looks like kilojoules is going to be a more appropriate unit, so I'm going to convert these to kilojoules. So this will be 0.82892 kilojoules. And this one would be 7.53957 kilojoules. And the first one is 0.9145 kilojoules. Just take the joules and divide by 1,000 to get kilojoules. So 0.9145 plus 6.02 plus 7.53957 plus 40.7 plus 0.82892. I'm getting 56.00299 kilojoules. How do we decide where to round that? We're adding, so we have to look at decimal place. So this is the second decimal place, this is second decimal place, this is the third, this is the first decimal place, and second. So this is the one that has the fewest number of decimal places. So we should round this off to the nearest tenth, and we're going to say this is 56.0 kilojoules of energy. Any questions? So you should be able to do a calculation like that for any substance. I expect you to know melting and boiling points for water. If it was something else like lead or something, I'd give you the information about what is the temperature of the melting point and the boiling point. And you would need to be given specific heat capacities, heats of vaporization, and fusion. We can do a problem where we go the whole range, or we could start at some temperature and just finish melting, or there's all kinds of other combinations. You could go backwards, how much energy is released when this amount of steam condenses and freezes, etc. Okay, but the idea is all the same. Make a picture so that you can refer to it and not get lost, and then do the calculation for each individual line segment.